Thanks, Dave. First, I want to thank organizers, particularly Weizhu and Weiqing, for organizing this wonderful workshop. It's a truly interdisciplinary workshop. You have speakers from experiments and also mathematicians. So this morning that the talks are all on experiments. Okay, I was thinking it would be great if all this can be done by numerical simulation, right? But this is easy to say than done, and I think the problem is very complicated. The model may not be easy to set up, and or the problem can be very expensive to simulate. So mathematicians have a lot of work to do. So I'm going to talk about this threshold dynamics method, and this is also a numerical. So this is a numerical method talk. So this is a numerical method for simulate interface motion. Okay. So I will try first introduce. Let me. Okay. Threshold dynamics method for interface motion on solid surfaces. Okay, so this can be applied to wetting problem that this morning several talks on this kind of a problem. And then for this method, then we also did some analysis on contact line behavior, okay, for this method. So this is joint work with Xiaoping and Wang who are here, and they did all the work, and then Sidong Jiang from NJIT, who is expert on fast multiple and non-uniform FFT. So we try to implement this using boundary integral method. So it speeds up simulation tremendously. Okay? And then if it turns out this method can also be applied to image segmentation. Okay? It's because image segmentation is also an interface problem, or at least can be formulated as an interface problem. So the threshold dynamics method was developed for simulating this so-called motion by mean curvature. Okay? Motion by mean curvature means if you start with some curve, okay, closed curve, then the curve moves with velocity that is proportional to the curvature. Okay? So that's motion by mean curvature. So under this motion, then the curve will turn into circular and then shrinks. Okay? Of course, you can also look at for a fluid problem. It will be a volume preserving interface motion. Okay? So how do you simulate this problem? Of course, you can do it directly, and you have a curve. You parameterize your curve, and you can compute the curvature, and then you move your marker points, and so on. So you can do it directly. But this you sometimes have a problem of, in particular, when you have a topological change, then this would give you some trouble. So there's a method developed by, introduced by MBO, Merriman, Benz, and Osher in '92. Okay, so the idea is to look at this problem based on Allen-Kane equation. Okay, because this Allen-Kane equation, if there is a small parameter epsilon, okay, which measures the interface thickness, and then you look at the sharp interface limit of Allen-Kane equation, and the sharp interface limit converge to to motion by mean curvature. Okay, so you can simulate the motion by mean curvature using Allen-Kane as an approximation. Okay, and of course this is a nonlinear problem. Okay, because F is a double well potential. Okay, and then you if you do direct simulation of Allen-Kane equation, you need to resolve thickness, interface thickness, which is of order epsilon. Okay, so the idea of MBO threshold dynamics is that instead of solving this Allen-Kane equation directly, you split this into two steps. Okay, in the first step, you solve a heat equation. Okay, with the initial data is a characteristic function of domain D. Okay, you start with a domain D, and then the characteristic function is 0 and 1. Okay, on inside domain is 1, outside is 0. This you use it's your initial condition. You solve the heat equation for one step. Okay, we all know that for heat equation after one step everything becomes smooth. Okay, with this heat equation, okay, the exact solution becomes smooth immediately. And then in the second step, you solve this ODE. Okay. After the smoothing, okay, so the first step is linear diffusion. It gives you a smooth solution. Then you solve the second ODE, which actually in this case, for this particular double well potential, you have exact solution. Okay? As epsilon goes to 0, this turns into 0 and 1. Okay? So it turns into a thresholding. So depending on your initial condition, if phi is bigger than half, then it goes to 1, and less than half goes to 0. So this step, actually, you don't have to solve. You just do thresholding. Okay? If the initial condition is after the first step, okay? If the value is bigger than half, this will give you 1. If value is less than half, it gives you 0. So combining this step, you start with a characteristic function, and you end up with a characteristic function. So therefore, your domain becomes a new domain. Okay, and you can show that because there is a time step here in step 1, and delta t goes to 0. This actually you can prove that this converges to motion by mean curvature. So therefore, instead of solving the nonlinear Allen-Kane equation, you turn this into two steps. One is heat equation, and one is simple thresholding. Okay? And that gives you the motion by mean curvature. So it's also called diffusion-generated motion of interface. Okay? Because
the order, or?
The order is delta t. Yeah. So you have two steps. The first step is solution of a heat equation, which is given by convolution of a heat kernel with the characteristic function. The second step is a simple thresholding. So you update your domain this way, and then that your interface moves. Okay, and you can show this is motion by mean curvature. And as you can see, this is very easy. A very simple numerical method, and very efficient because it's unconditionally stable. It's the computational cost is optimal because it's the heat kernel convolution. So this can be done by FFT. Okay? So you have n log n. Each iteration, you have n log n, okay, computational cost. And this because the interface is implicitly represented, so this allows for topological change also. Okay. Actually, this is this can be generalized to more system. For example, if you consider the general Ginzburger-Landau free energy, okay, where U is a vector, okay, so it's from Rn to Rm, okay, but with it's a W is a multi-well potential, and when epsilon goes to 0, you have this asymptotic limit. Always gives you some kind of defects or singularities. Okay, and so the dynamics gives you the motion of those singularities. Okay, so in the first case, when U is a scalar, then this is what we just saw, Allen-Kane equation. So you have interface. Okay, this should be -1 and +1. Okay, or 0 or 1. Okay, and then in the if U is a vector, 2 by 2, say, 2 vector, and the domain is 2 dimension, and then this is the singularity is vertex. Okay, so when epsilon goes to 0, and you can derive dynamics of vertex dynamics, and Fang Hua Ling did a lot of work in this for this system, and so you can also generalize to 3 dimension. N is 3, okay, and so it will be line defects, okay, filaments, and so on. Okay, of course there are even matrix can generalize to matrix problem. Okay, so this morning we see a lot of experiments. Okay, so you want to look at the behavior of a drop on superhydrophobic surfaces. Okay, as we can see that the surface is actually has this very rough structure. Okay, so because the original MBO method was developed for closed interface, okay, without solid boundary. Okay, so the question is, can we use the same idea for a problem with solid surface, and so that we can apply this to the Wettin problem, okay, and in particular Wettin problem for rough surface, okay, either geometrically rough or chemically rough. Okay. And also you want your method to be insensitive to those roughness. Okay. So if you have a rough surface, then say if you want to look at the equilibrium structure, equilibrium of the droplet, it's no longer like in the closed surface. It would be always circular, right, or spherical. But on the rough surface, it's the shape is it depends on the roughness of the surface. Okay. So here you have so-called Young's equation for equilibrium of droplet on the surface. So this is for mathematician, right? For a physicist, those are obvious concept. So there's a Young's equation that determines the contact angle, okay, of an interface with with solid surface if the surface is flat, and then 3 surface tension coefficient determines the angle. If contact angle is less than 90 degrees, it's hydrophilic. Okay? Bigger than 90 degrees, it's hydrophobic. And you have a limiting case when contact angle is 0 and 180 degrees. Okay? So this is a super hydrophobic surface if the contact angle is close to 180 degrees. Okay? equilibrium state of a drop on the surface is determined by the surface energy. Okay. So this you can write in this case, if it is chemically rough and geometrically rough, you can simply calculate the surface area multiplied by surface tension coefficients, and on the solid, you can also calculate their respective energy. Okay? And then the problem becomes minimizing this total energy, total interface energy. Okay, and of course you can also use a diffusive interface model. Okay, by using this Allen-Kahn free energy, okay, plus the surface energy. Okay, and then you can show that when epsilon goes to 0, this also converges to the interface energy that we described here. Okay, but in this case, the problem becomes smooth. Okay, if you minimize this total interface energy, the problem is smooth. Okay, so therefore, mathematically it's easier, and numerically it's also easier because the problem is smooth. I mentioned that can we use the threshold dynamics method for problem with solid boundary, okay, when interface intersect with solid boundary. Okay, and okay, so of course, if you can directly generalize the original MBO for this problem. Again, split the problem into 2 steps. Okay, the first step is a heat equation, but now you need to solve the heat equation on the bounded domain with a boundary, and the boundary can be rough. Okay, with also this boundary condition, okay, wetting boundary condition. So this problem is no longer easy to solve, okay, because you don't have a heat kernel here, okay, for a bounded domain, and in particular, the boundary condition is not that simple. Okay, so you don't have a heat kernel formulation for this. Okay, so you have to solve, even though it's a linear equation. Well, the boundary condition can be nonlinear. But the equation is linear. Okay, so if you have a very efficient method for solving heat equation on the bounded domain with rough boundary, that's fine also. Okay, but most people will not be able to do that. Okay, this is not the way to use, not our way to use to generalize the problem. Okay, our approach is to use a different formulation. It is well known that the interface between 2 domains, D1 and D2 in this case, okay, the length of in 2 dimensions, the length of the interface can be approximated by a heat kernel convolution with the respective characteristic functions. Okay, so I have a D1, D2. You convolution with say D2, and you multiply by D1 and you integrate, and then you scale it, okay, with the square root of delta t. That's an approximation of the interface length. Okay, in 3D, it will be approximation of interface area. Okay, and this can be this is proved rigorously. Okay, so when delta t goes to the heat kernel, delta t goes to 0. This converges to the interface length, and So the idea was used by Asadogalo and Otto to develop structural dynamics for unphased motion by mean curvature flow. Okay? So here what we need to do is to, because we have three interface energy, right? So you just have to approximate each energy. Okay, so this is the first. We have three terms here. The first term is the interface energy between liquid and vapor. Okay, so this is the blue one. Blue curve is approximated by this heat kernel convolution multiplied by the surface tension coefficient, and the second term is the surface energy between D1 and D3. Okay, so it's part of this green part. Okay, so now, so in this case, we need to extend our domain into to include the solid surface, solid part as D3. Okay. So here, but D3 is solid, so it doesn't change. Okay, it doesn't change. So we have three terms, and then the minimization problem becomes minimizing this total interface energy. Okay, over the domain. Okay, if you denote U1 as the characteristic function of D1, U2 as the characteristic function of D2, then you are minimizing this total interface energy. Okay, in the space of U1, U2, okay, which are characteristic functions. Okay, and also you have this area conservation. Okay, so you preserve the volume of the liquid, okay, for example. So, but this problem is non-convex, okay, because the domain is a non-convex domain. But you can relax this condition, okay, to a convex optimization convex domain by allowing that the instead of characteristic functions, but you look at the U1, U2 functions between 0 and 1. Okay, but with the constraint that they add up to 1 and the volume given, okay, of U1, integration of U1 is given. Okay, and you can show that the minimum of the total energy over that convex set, okay, the minimum is actually attained on the original set. Okay, so therefore, this although you are minimizing over an enlarged domain, but the minimum is attained at the original domain, and this also can be proved. Okay, so now the problem becomes finding minimum of this functional. So the idea is to like Newton's method, you linearize the original functional, and you find the minimizer at the over that domain. Okay, because it's a linearized functional, the minimum actually is easy to obtain. Okay, and that leads to the threshold dynamics method. Okay, so in each step, it's again a convolution. Okay, with characteristic functions, and followed by thresholding. Okay, of course it's a volume preserving thresholding. Okay, and you can show that first of all, minimum is attained by the characteristic functions, and also you can prove. Okay, so this is the algorithm. Okay, you have initial convolution step followed by thresholding. Okay, of course, for volume preserving thresholding, you need to have some efficient algorithm also. Okay, and then you can prove that this sequence of the iteration decays, okay, decays in each step. So it's going to converge to a minimum. So here's a simple example that you start with. You start with some arbitrary curve. With in particular, there's a I think it's a 60-degree contact angle case. Okay, so you can see that it converges to the exact solution, and I actually have the you can verify the convergence rate is delta t. Okay, but near the contact point, okay, near the contact point, you can see some deviation from the 60-degree angle. But this can be improved as you increase the resolution here. And but there is a deviation. You can understand this deviation by looking at the problem more carefully. Okay. So as you can see that our NH can be approximated by three heat kernel approximated by heat kernel convolution, where I use, in this case, I use H for the delta T. Okay, so each NH converges to the exact NH as H goes to 0. Okay, and then you add up. Okay, but in fact, this 3H doesn't have to be the same, right? As long as they are going to 0. Okay, this, because they all converge to the surface energy. So this is actually the reason that why there's a deviation of the contact angle, okay, from the exact contact angle. So because if the contact angle is less than 90 degrees, from this picture you can see that in this case, the interface energy, okay, of liquid vapor and solid liquid underestimated, okay, by the heat kernel convolution, because there is a heat kernel has a thickness of H. Okay, and here you can see that there's this part is the band. There's supposed to be a band. So this two underestimated, but the solid vapor part is overestimated. Okay, and then the contact angle is the ratio of this. One is underestimated, one is overestimated, and the ratio, even as H goes to 0, this deviation is not decreasing. Okay, so you always have a deviation. Okay, so to correct that, okay, one can instead of choosing the same H for the heat kernel, okay, you can choose a different. Okay, you allow this H to be different for different NH term. Here we use it for the two terms. Use the same H2 for the two terms involving solid part. Okay, and then you can try to look at the asymptotic behavior of the interface. Okay, in each thresholding steps. Okay, so this is the function that we use for the thresholding. So I have a solid boundary here, okay, which is the x2. I have a d3 here. So you want to see how interface moves along this solid surface. Okay, so therefore you look at the asymptotic behavior of this function at the x1 equal to 0. So therefore it's the point here. Okay, and then you do the asymptotics as h. So you assume h2 is lambda h1. And then you do the asymptotics. Then the leading order gives you this behavior. So the calculation is pretty tedious because you have to estimate the integral because the energy is integration, so you have to estimate. So it's tedious, but the leading order term can be written down here. Okay. So in the thresholding, okay, volume preserving thresholding, so you have to choose the delta to correct delta to do the thresholding, and this shows that to balance the two sides, and this red part has to be 0, okay, and has to be leading term has to be 0, and the flow part also has to be 0. And this gives you that in order to have contact angle to be the original Young's angle, you need to choose lambda to be this number. Okay? And this is solving, this you solve from here. Okay? Let this equal to 0. And then the next order term gives you the velocity of the contact point, okay? Which is, again, related to the curvature over sine theta. So it's the interface motion projected along the solid surface. Okay. So that gives you this analysis also gives you the contact point dynamics. Okay? Contact point dynamics. And so this is how you show that indeed you're by using this NH formulation, it does improve. Okay. So by comparing this with the if you choose H1 equal to H2, okay. So it does improve. Okay. But still, we still have this. Originally, I thought this is going to be improved from square root of delta t to first order, but it turns out that numerically it's still not. Okay, but at least it gives you some better contact point, contact angle behavior, and this is in the hydrophobic case. Okay, so we have this is a summary of this part, and so I mentioned that we have a boundary integral formulation implementation of this threshold dynamics method, and this is based on this spectral approximation of heat kernel. And then with non-uniform FFT, and so on. So in this case, even for a 3D problem, okay, using this non-uniform FFT, so this is a initial surface, and then eventually it turns into a spherical surface. So we can do this 3D simulation on the laptop with 1 hour. Okay, so that's very, very fast. Okay. If you do it using phase field method, it will take days, okay, to do this simulation. Okay, okay, so I want to mention some application for image segmentation. Image segmentation means that I give you an image, okay. Then you want to identify objects in the image, right? So identify boundary of the object. So it's an interface problem, okay? So like in this case, eventually you want to identify the airplane or a person, and so on. So again, it's an interface problem. So it's well known that this can be image segmentation problem can also be formulated into a minimizing certain functional. Okay, where in this this is so-called piecewise constant Mumford shot. Okay, in the case of two-phase segmentation problem, you have constant C1 and C2. Okay, say it's 0 and 1. Okay, 0 and 1, and it has to be sufficiently close to the original image F, and in this constant Mumford shot, you have a penalty of penalty is the perimeter of the domain, okay, of one phase, one of the phase. Okay, so there, it's a lot of numerical method for solving this. Okay, it turns out this because again this is perimeter term here where we can use heat kernel convolution to approximate that. So this can be this problem can be formulated into optimization of threshold dynamics method. Okay, and there was a early work on using threshold dynamics based on the Alenkine type equation, because the interface energy can be approximated by the Alenkine Frenet functional. So you're solving a Alenkine type of equation, and if you do it by MBO, you need to solve this heat equation, but with non-constant coefficients. Okay, so this is again not very efficient it's not as direct as, I mean, there's no heat kernel here. So again, our approach is to approximate the perimeter by this heat kernel convolution, and then you have total multi-phase energy. Okay, can be formulated in an exactly similar way as the weighting problem. Okay, or interface problem. Okay, so this again can be easily generalized to well, the threshold dynamics method can be easily generalized to this problem. So it's in fact it's exactly the same. Okay, it's that the energy term is different. Okay, except so again it's a convolution of heat kernel in one step and thresholding in the other step. Okay. And you have energy decaying property also. Okay. So here is an example. So where you start with some initial contour, okay, initial curve. Okay, it's quickly evolved into the boundary of the object. Okay, so this is what you need to do. And for this 256 by 256 problem, on the laptop, it takes 0.1 second. Okay, so it's real-time simulation. Okay, you look at the energy plot. Okay, I think people here are not very interested in this image segmentation problem, but this is it shows that the method is very fast. Okay, so you have again initial curve here, so they'll evolve into the boundary of those objects. Okay. And this is multi-phase. Okay, so I have 4 phase here. Okay, because different color has different as a different phase. Okay. So that's the end of the my talk. So we apply this method to particularly for this audience as the method for interface motion on the boundary. So here one thing that remark that I want to add is that we didn't incorporate the fluid property here. Okay, because that would make it much more complicated. Okay, because it's here it's still energy driven. Okay, so interface energy driven, but there's no fluid. But this can be we are working on that. So you can combine this with Navier-Stokes equation with a solid boundary, and this is doable. Okay, we're working on this. Okay, that's. Thank you.
Questions? I got a little confused about the convergence rate of the interface.
Yeah.
So you discretize, so there's a step size someplace.
Yeah.
So at what rate does the interface converge?
Delta t. It's first order.
But in space.
Oh, in space, you discretize. It's whatever. It's in our case, it's spectral. It's spectral convergence in space. Okay, but the to converge to motion by mean curvature, this is controlled by delta t. Yeah.
So you have a discontinuity, as I understood the method, there's a discontinuity in the interface.
Yeah.
Every diffusion finds
Right. Right.
still converges? Spectral?
Yeah. So basically, it's a sharp interface method. Okay. So every step you obtain a sharp interface. Okay. But by no, there's no infinite derivative. It's heat kernel convolution because heat kernel smooths out everything, right? So yeah.
But you always have at your time, whatever you're at, you always have a discontinuity.
Right. So this is heat kernel convolution, right? Heat kernel convolution of your so this is done by FFT.
Right. So
Yeah.
On the same question is, there is the thresholding.
Yeah.
You have the thresholding on your Fourier, on your series.
Yeah.
So there's be a delta x coming in there somehow. You could threshold on a finite difference grid, or you can threshold on a
Yeah, on finite difference. Yes, thresholding it's also.
Threshold,
Yeah. Okay. Right.
There must be a spatial.
You're right. Yeah. Yeah. Thresholding does introduce space resolution. Yeah.
I think that's the question.
Okay. You're right. You're right. Yeah. That's true. Yeah.
Can you conserve the volume?
Yeah. I skipped that there. I suppose I don't know why I didn't put. So we have a way of volume preserving thresholding. Okay. Usually it's done by iteration. You find a threshold value, and then you iterate until it's correct. But for us, we use this quick sort algorithm. In fact, no iteration is needed. Okay? It's by counting the number of grid points. Okay, because if you only want the first order accuracy, then your volume is equal to number of grid points that is bigger than certain threshold value, right? You just do it there, so you don't have to do iteration. You just have to count the numbers. Okay, the largest value of the after diffusion.
You were fixing things a bit by taking H1 and H2.
Yeah.
And that's at the diffusion state. Can you, quote unquote, fix things more by doing something weighted at the thresholding state?
Yeah, we are not doing that. That might. Did we consider that? Yeah. Yeah. Right. You might. Yeah. Okay. No, we are not doing that, but yeah, it could be. Yeah. Yeah. Right. Yeah. That's true.
So you
But you have to do it locally at the contact point. Yeah. 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 Yeah.
So you mentioned that the work you're doing now is trying to build in fluid dynamics.
Yeah.
And therefore, you have all the interior to worry about. If you do a problem instead, which is more like a surface diffusion problem, where everything's still on the surface, but now you've done a equation of motion goes like a Laplacian curvature.
Yeah. You can.
Is it easy to make that change?
For surface diffusion.
You're right. Instead of just
Yeah.
motion by mean curvature.
Right, yeah, you can do that. You just I mean, actually, there are works on this. You just change the kernel. Okay, you have to do the derivation so that this converge to surface motion. I mean, surface diffusion. Yeah, but I think the accuracy is the convergence accuracy is even lower. If you, yeah. But theoretically, yes.